In this video, you will learn how to perform time series forecasting that is used to solve sequence problems. Time series forecasting refers to the type of problems where we have to predict an outcome based on time dependent inputs. Typical example of time series is stock market data where stock prices change with time. Similarly, the hourly temperature of a particular place also changes and can also be considered as time series data. Time series data is basically a sequence of data, hence, time series problems are often referred to as sequence problems. Recurrent neutral networks (RNN) have been proven to efficiently solve sequence problems, particularly long short-term memory network (LSTM), which is a variation of RNN, which is currently being used in a variety of domains to solve sequence problems. Type of sequence problems. Sequence problems can be broadly categorized into following categories. One-to-one, where this is there is one input and output. Typical example to a one-to-one sequence problem is the case where you have an image and you want to predict a single label for the image. Many to one. In many to one sequence problems, we have a sequence of data as input and we have to predict a single output. Text classification is a prime example of many-to-one sequence problems where we have an input sequence of words and we want to predict a single output tag. One-to-many. In one-to-many sequence problems, we have single input and a sequence of outputs. A typical example is an image and its corresponding description. Many-to-many. Many-to-many sequence problems have involve a sequence input and a sequence output. For instance, stock prices of 7 days as input and stock prices of next 7 days as outputs. Chatbots are also an example of many-to-one sequence problems where a text sequence is an input and another text sequence is the output. This video is part 1 of the series. In this video, we will see how LSTM and its different variants can be used to solve one-to-one and many-to-one sequence problems. In the next part of the series, we will see how to solve one-to-many and many-to-one many sequence problems. We will be working with Python's Keras library. After watching this video, you will be able to solve problems like stock price prediction, weather prediction, etc. based on historic data. Since text is also a sequence of words, the knowledge gained in this video can be used to solve natural language processing tasks such as text classification, language generation, etc. Thank you.
In previous video, we saw how to solve one-to-one sequence problems with LSTM. In a one-to-one sequence problem, each example consists of single time step of one or multiple features. Data with single time step cannot be considered sequence data in a real sense. Densely connected neural networks have been proven to perform better with single time step data. Real sequence data consists of multiple steps such as stock market prices of past 7 days, a sentence containing multiple words, and so on. In this video, we will see how to solve many-to-one sequence problems. In many-to-one sequence problems, each input sample has more than one time step. However, the output consists of a single element. Each time step in the input can have one or more features. We will start with many-to-one sequence problems having one feature. Then we will see how to solve many-to-one problems where input time steps have multiple features. Many-to-time sequence problems with a single feature. Let's first create the dataset. A dataset will consist of 15 samples. Each sample will have 3 time steps, where each time step consists of a single feature, i.e. a number. That is a number. The outputs for each sample, will be the sum of the numbers in each of these 3 time steps. For instance, if our sample consists a sequence 4, 5, 6, the output will be 10. That is 4 plus 5 plus 6. Creating the dataset. Let's first create a list of integers from 1 to 45. Since we want 15 samples in our dataset, we will reshape the list of integers containing the first 45 integers. Now let's run this. This is our dataset. In the output, you should see the first 45 integers. Yes, we have got first 45 integers. We can reshape it into number of samples, time steps, and features using this function that I'm going to show. The above script converts the list X into three-dimensional with 15 samples, 3 time steps, and 1 feature. The script also prints the reshaped data as we have the reshaped data. We have converted our input data into the right format. Now let's create our output vector. As I said earlier, each element in the output will be equal to the sum of the values in the time steps in the corresponding input sample. So let's create our output vector. And we have got it. Output array y looks like this. Now let's do a solution via simple LSTM. Let's create our model with one LSTM layer. This is our simple LSTM model. Now we have to, for the following script, we are going to take a script that trains our model. Now let's run this. Now that has created our model, trained our model. Once the model is trained, we can use it to make the predictions and the data points. Let's predict the output for the number sequence 50, 51, 52. The actual output should be 153. The following script converts our test points into three-dimensional shape and then predicts the output. So it has trained our model. So this is used to predict the output. The output is 152. So we got 152.6841, which is around 1 point less than the output value of 153. Now let's create a complex LSTM with multiple layers and see if we can get better results. So let's execute a script. So this is our script. Now let's run it. Let's test our model in the test sequence. Now let's see the output. We got a little lesser than last time, which the answer I got here is 152.54907, which is a little worse than last time, and we have only 0.5 difference from the answer 153. Now let's do a solution via bidirectional LSTM. Bidirectional LSTM is a type of LSTM which learns from the input sequence from both forward and backward directions. The final sequence interpretation of is the concatenation of both forward and backward learning passes. Let's see if we can get better results with bidirectional LSTMs. The following script we are going to use builds up. The following script trains the model and makes prediction on this test sequence, which is 50, 51, and 52. Now let's see what we got. The result I got is 152.46, which is just a fraction short of the actual result. Therefore, we can conclude for the data set that bidirectional LSTM with a single layer outperforms the single player, but our unidirectional also did well. Then need to see one sequence problems with multiple features. In many to one sequence problems, we have an input where each time step consists of multiple features. The output can be a single value or multiple value, one per feature in input time step. We will cover both the cases in this video. Creating the dataset. Our dataset will also contain 15 samples. Each will contain 3 time steps, but it will have 2 features. So let's create 2 lists, with each will contain multiples of 3 until 135. And the second list will contain multiples of 5 until 225. The second list also will contain 45 elements, like the first one. So let's create a script to create these 2 lists. Let's run this. So we have got the one feature in the time sample. The aggregated data set can be created by joining the 2 lists as shown. Now now let's run this. As you have seen, it has made it aggregated data set till 225 of the second list and the first list. We need to reshape our data into 3 dimensions so that it can be used by LSTM. We have 45 rows in total and 2 columns in our dataset. We will reshape our dataset into 15 samples, 3 time steps and 2 features. Let's run this. It has made it into following outputs, the 15 samples and the following outputs. The output will also have 15 values corresponding to the 15 input samples. Each value in the output will be the sum of the 2 features in the third time step of each input sample. For instance, the third time step of the first sample will have features 9 and 15, hence the output will be 24. Similarly, the 2 features on the value of the third time step of the second sample are 18 and 30, and the corresponding output will be 48, and so on. The following. Now let's do a solution via simple STM. Now let's do a solution via simple STM. Now let's run this. It has made it into a system and it's training on 12 samples. Let's wait for some time. I think it's done. Next, what we're going to do is we're going to test data point. We're going to create a test data point and use our model to make prediction on the test. Let's run this. So the sum of the 2 features is the time step of the input 14 plus 61 75. Our model layer predicted 73.5, which is 26.085997, which is okay. Solution via stacked LSTM. The following script trains a stacked LSTM and makes prediction on test point.
it has predicted 24, so our simple stacked LSTM is better than our stacked LSTM, which is overfitting. Now let's do a solution via bidirectional LSTM. Let's take a training script for simple bidirectional LSTM to go along with the code. So now let's see the output. The output we got is 90, which is very far. LSTM this bidirectional seems to be performing a little low. Until now, we have predicted single values based on multiple features values from different time steps. There is another case of many to one sequences where we want to predict one value for each feature in the time step. For instance, the dataset we used to predict has 3 time steps and each time step has 2 features. We may want to predict individual value for each feature series. The following example makes it clear. Suppose we have the following input. In the output, we want one time step with 2 features. You can see the first value in the output is a continuation of the first series, of the second value is the continuation of the second series. We can solve such problems by simply changing the number of neurons in the output dense layer to the number of features that we want in the output. However, first we need to update our output y. The input vector will remain the same. The RAM code creates it like this. Above script creates the output vector and prints it in the console. Output looks like this starting from 4th value. Let's now train a simple stacked LSTM and bidirectional LSTM networks on our dataset. The following script trains a simple LSTM that we're going to run. Let's run this. It's training the samples. Next, what we're going to do, the output is supposed to be 29 and 48. Our output module predicted 29.28, which is very close, and 48.51. That is really a little, which is pretty close. Let's now train a stacked LSTM and predict the output of further test data point. So let's run this. The output we got is 29.052 and 48.61, which is really close. First, now we can train a bidirectional LSTM and make the prediction on the test point. We got 29.40, 48.98, which, and you can see once again that the bidirectional LSTM makes the most accurate prediction. In this, we have made a conclusion that simple neural networks are not suitable for solving sequence problems, since in sequence problems, in addition to current input, I need to keep a track of the previous inputs as well. Neural networks with short-term memory are suited to solve sequence problems. LSTM is one such network.
In this video, we saw how different variations of the LSTM algorithm can be used to solve one-to-one and many-to-one sequence problems. This is the first part of the video. In the next part, we will see how to solve one-to-many and many-to-many sequence problems. You'll